Eddy currents. A changing magnetic field induces a swirling current in a conductor. If the conductor and magnetic field are in relative motion, the magnetic force on charged particles in the conductor causing circulating currents. These currents are called eddy currents. Eddy currents give rise to magnetic fields that oppose any external change in the magnetic field. In a nutshell, when the magnetic flux through a large piece of conducting material changes, induced currents appear in the material. These currents are called eddy currents. If you have a magnet and you have a loop that has absolutely no current in it, and you want to move this through the field, what you will observe is no force is needed to pull the loop when the wires are outside the magnetic field. However, when the wires are actually inside the magnetic field, a pull force is needed to balance the magnetic force on the induced current. Eddy currents are induced when metal sheet is pulled through the magnetic field. Now, these eddy currents flowing in the material will generate their own secondary magnetic fields, which will oppose the coil's primary magnetic field. So what's the use of this? Well, crack detection is one of the primary uses of eddy current. Cracks causes a disruption in the circular flow of eddy currents and weaken their intensity. So as soon as you come across a crack, you will figure it will be picked up, because there will be a disruption in the eddy currents that are produced in the sheet metals. Other applications of eddy currents include the magnetic braking system. It is often used in aviation industries to detect material loss due to corrosion and erosion way faster than through a naked eye. And it is also very helpful to measure material thicknesses, way better than with a naked eye. More applications of eddy currents include magnetic leviation or maglev trains that use eddy currents in order to go really, really fast and reduce the friction between the train and the track. Induction stoves are another example. An AC current in the coil on the stovetop produces a changing magnetic field at the bottom of the metallic pan. The changing magnetic field gives rise to a current in the bottom of the pan. Because the pan has resistance, the current heats the pan. If the coil in the stove has low resistance, it doesn't get hot, but the pan does. So an insulator won't heat up on an induction stove.